Welcome to Ready to Drive. Imagine you are flying in that plane and the pilot is preparing for descent. I'll give you two scenarios and you pick the one that you would prefer to experience. So there's this landing pattern and there's that one. I imagine you would have chosen the former. Why? Because it's less steep, of course. The latter one, you'd have to descend pretty rapidly to cover that distance in the same time. So this concept of steepness is a very important concept in the real world, everywhere from the descent of a plane and the design of stairs and handicap ramps to the building of roads and the climbing of mountains. In this video, we are introduced to the mathematical concept of slope, which is the most common measure of steepness. While we start with real-world examples like the one we just saw, we then move to the coordinate plane and these definitions of slope, which are very important for algebra. Along the way, we learn how to distinguish between lines with positive, negative, zero, and undefined slopes. So without further ado, let's dive right in. So let's examine how we could measure the steepness of the plane's descent. So there we go. We have a feeling that, well, we know we could kind of describe the angle which it goes down, but slope takes a look at the measure of steepness in a different way. So what you first have to establish is, here we have the plane is 100 miles, let's say it's 100 miles from where the airport where it's landing, and it is flying at 30,000 feet and begins its descent. So in the course of 100 miles, it has to descend by 30,000 feet. Slope is defined to be the vertical change over the horizontal change. So in this case, we see that the vertical change is the 30,000 feet. So if we take 30,000, I'm going to just keep the units with it. 30,000 feet per basically every 100 miles, that defines the slope. And we can simplify that, dividing top and bottom by 100, so 300 feet for every 1 mile. Now this version of slope is more like slope thought of as a rate. Now you're going to see that slope more typically is treated as a ratio, but this is how this reads. For every 1 mile the plane travels horizontally, it descends by 300 feet. And you literally could see that if you just break this down, if you think about just how much it goes. So if you travel 1 mile, whatever 1 mile is, it would go down 300 feet. And that's like a smaller version of this triangle here. It's the same ratio. So every 1 mile it drops 300 feet. Therefore, in 100 miles, it would drop 30,000 feet. Now, the other way to think about this is to get the units to be the same. And most often when we're dealing with slope, that's exactly what we are going to require. So let's take that 300 feet over 1 mile, that simplified version, and let's turn that to 300 feet and turn 1 mile is 5,280 feet. Well, now you'll notice that the units cancel and you're left with a ratio. It's approximately 0.06 over 1. So this is a ratio because the units cancel out. The units don't really matter, and that gives us some important information. It says for every 1 unit the plane travels horizontally, it descends by, well, 0.057 units, approximately 0.06. So that could be for every mile, for every foot, for every kilometer. The ratio is always the same. And the important thing to realize is the nice thing about keeping the units the same is that you can express this as a percent. So therefore you can think of this as the vertical descent will always be 6% of whatever the horizontal distance traveled is. So now we understand slope as a ratio, and that can also be represented as a percent. We'll better understand this warning road sign, which is warning trucks either going uphill or downhill. In both cases, it can be difficult and dangerous, that the slope of the road is 12%. That's also known as the gradient of the road. And we know that slope is vertical change over horizontal change. So 12% means 12 for every 100. And we know also that the units could be whatever. It could be feet over feet, miles over miles, etc. Now, you might think to yourself, well, how can the vertical change, therefore, is 12% of the horizontal change? And that triangle, that hill in the picture doesn't look to scale. So I actually drew one to scale. And I made it so that the base corresponded to 100 and the height corresponded to 12 of that triangle. So it now 12% doesn't sound very steep, but it really is for trucks, especially if it's a long hill going uphill. They lose a lot of speed, and going downhill they have to worry about braking. So I also want to show you that 12 over 100, that can be reduced to 6 over 50. And the nice thing about that is if you can see this in the triangle. If you cut 100 in two, so you make this 50 here, well, to keep the same shape triangle, in terms of similar triangles, this would have to cut the 12 in half to be 6. And similarly, if you simplify that a little further, 3 over 25, so if I cut the 50 in half, and let's see about there, and I make this 25, then I'd have to cut the 6 in half and make that 3. So you can see whatever ratio you use, the percent, 12% still stays the same. So that's an example of slope in everyday life. Now, in an Algebra 1 course where you're really going to meet slope most of the time is on the coordinate plane. So let's take, and what we're usually talking about is the slope of a line. You can consider this like a hill, the slope of the hill. And here we go. So we know that slope is now, instead of saying vertical change over horizontal change, notice that the vertical change, since vertically we have the y-axis, we call the vertical change delta y, and the horizontal change delta x. And sometimes that's even referred to as the rise over the run. So delta y is the rise and delta x is the run. So we can see for this, let's have a look here now. We can actually, if we just create a triangle, so let me just, with these 2 points, we have the coordinates of 2 points and we're trying to find the slope. We could pick any 2 points on this line to calculate the slope, but I've picked the ones that are shown to us here. So we could have also used like this point here, which looks like it's at 1, 2. So if we do that, we see that the rise, which is this distance, see, we can just count the boxes, it's 2. And we can see that the run, let's see, 1, 2, 3, 4, 5, 6, the run is 6. So therefore the rise over the run would be 2 over 6. And that simplifies to 1/3, but I'd like just to keep it like that for now because I want to show you a pattern. So what if you don't want to count boxes? What if the coordinates were like -100, 5 and 1,000, 333? There must be a better way. So let's think about where this 2 came from here. So that 2 is, if you think about it, it can be got by just taking the y-coordinate of the higher point, 3, and subtracting the y-coordinate of the lower point. So 2, this 2 up here, is really just 3 minus 1. And now, what about the 6? Could the 6 be gotten the same way? Well, the 6, if you look at the x-coordinate of the point furthermost to the right, it's 4. And the x-coordinate of this point to the left is -2. And if you do 4 take away -2, you do indeed, hold on, excuse me there, you do 4 take away -2, you do indeed get 6. So this leads us to an important understanding, is that delta y is really just achieved by taking the difference in the y-coordinates of the 2 points, and delta x is just the difference in the x-coordinates. So let's generalize that now. So let's kind of superimpose here. I'm going to have to get rid of this here, previous work, and let's call this now, let's call this point, give it a more generic label. So let's call that x1, y1 and x2, y2. So they're both xy points, but we need to distinguish between the pair of them. So think of this x1, y1 as the first point, and this is the second point. So if we now, let's create a little right triangle so we can think about the slope. And we have here that if we would like to know what delta y is, it's the difference in the y coordinates. So the y coordinates, that's y2 is the height of that point, y1 is the height of this point, and therefore y2 minus y1 would give us the vertical change. And in terms of horizontally, so delta x, what is the horizontal change? Well, according to what it says there, it's a difference in the x coordinates. So this x coordinate is x2, this is x1. It doesn't matter if one or both of them are negative, it would still work out. And so delta x will be the change in the x coordinates, which will be x2 minus x1. And that leads us to the general formula for the slope between 2 points on the coordinate plane. It's the ratio y2 minus y1 over x2 minus x1. So for our first practice problem, we're just going to practice finding the slope of the line, passing through some pairs of points using the slope formula. So in terms of using the slope formula, it's helpful to identify the coordinates, distinguish between x1, y1 and x2, y2, and then it's a simple case of plugging in. So for the first one, so 5 minus 1, change in y coordinates over 0 minus negative 2. It is important that you subtract in the same order. You could call the points, you could have reversed the points and called this x2, y2, this x1, y1. It would still work. The signs would work out in the long run, but just be consistent. So that comes out to 4 over 2, which is just, comes out to 2. That's implied in the slope of 2 is 2 over 1. So here's a picture of it just to make sense of it. So 0, 5 is up here. And we are interested in, this looks like a pretty steep slope. Imagine driving a car up that. That's a slope of 200%. Because what's actually going on here is that the slope of 2 over 1 is every time you run over 1, you rise up 2. Run over 1, rise up 2, which is the same as saying run over 2, rise up 4. Okay, so let's look at the next example. So the slope is this. Eventually you won't need to label them, but let's do it for now. And then just apply the slope formula. So y2 minus y1, so minus 3 minus 1 over 4 minus negative 2 equals negative 4 over 6, or negative 2/3. Now, this is the first time we really met what what we mean by a negative slope. So to see that visually, let's graph the point 4, negative 3 is here. So this line is considered to have a negative slope. And if you can think about it as you move from left to right, if you were, as your x-coordinate goes from negative to positive, so imagine you were on this line and you were just walking along it, you would be moving downhill as x goes from left to right. So that's why we say the slope is negative. And how does that look? Well, the negative 2/3. So if we pop the negative with the 2 for a moment, all right, we think of it as going down 2 and then right 3. This is not very accurate. Excuse my line is not very good. Down 2, right 3. It's the same as going down 4, right 6. So distinguishing between lines that have positive and negative slope is very important. It makes a difference. So second practice problem, we'll find the slope of the line passing through some other pairs of points. So we're going to use negative 2, 1 again, and this time the point 3, 1. So this is the slope formula. Instead of labeling y2, y1, etc., we're just going to go straight into, let's just recognize that y2 minus y1 means you just subtract the y coordinates. So I'm going to put 1 minus 1 up there. Let me color code this to make it a little easier. And then x2 minus x1 is just going to be 3 minus negative 2. And that gives us 0. That's interesting. 0 over 5. which in fact is just 0. Any number, and if 0 divided by any number is always 0. So what does a line with a slope of 0 look like? Well, let's graph this point. -2, 1 is graphed already, and 3, 1 is here. And what this means, let's have a look. So this is, if we connect this, we have something, we're moving over 5 units to the right. So that is our, what we would call the run. But notice that we're not rising at all, right? So the slope, therefore, is 0. That's a horizontal line, and it makes sense that the slope is 0. Think about walking along that line. It's no effort whatsoever. So you can think of the slope as being a measure of how hard it is to, walk along the path. All right, so let's take these 2 points. Once again, we'll dive straight in and we'll just do the y-coordinates subtracted. So -4 minus 1. Let's put the equals, fraction bar, and then let's color coordinate. So this x-coordinate, you might sense that these are the same numbers. So we have a situation where we have, let's see, -5 over 0. So now the answer, any number divided by 0, is in fact, if you try that on your calculator, you'd get an error. It's undefined. You can't divide by 0. You don't know how many times 0 goes into any given number. So let's see what that looks like. Let's see the point, -2, -4. Look, it's directly underneath the original point. So what we have is a vertical line. And in this case, notice that the rise, the so-called rise, is -5, and the run is 0. So when the rise is -5, it means that you go down 5. So from your starting point down 5, but you don't run over any amount. So it's all rise, no run, and then you have a vertical line with an undefined slope. So here's the takeaway from this slide. A horizontal line has a slope of 0. A vertical line has a slope that is undefined because, again, think how hard it would be to drive up that or walk up that vertical line, except unless you're Spider-Man, it's basically impossible. So the slope is kind of infinite, so steep you can't even give a number to it. It's undefined. So for our last practice problem, we're going to practice graphing a line through a point with a given slope, because it is very important to know how to interpret a slope. So a slope of a -3/2. To get a negative answer, there were only 2 scenarios that were possible. Either the numerator was negative and the denominator was positive, or vice versa. Those are the only ways to get a negative answer. For a fraction, it couldn't be negative over negative because that would cancel out to make a positive. So let's consider the 2 situations. So here's the point. We're going to graph this line, but let's talk about slope first. So a slope of -3 over 2. Remember, slope is informally thought of as rise over run, and this is very helpful when graphing lines. So a rise of -3, negative means, rise usually means go up, but if it's negative, it means go down. And a run of 2 implied in that is a +2. And how do we interpret that? The instructions that the slope gives us is to move down 3, right 2 from your starting point. So let's go to our starting point, which is right here, and let's go down 3. So 1, 2, 3, right 2, and we get us a point here. And we can continue with that pattern, down 3, 1, 2, 3, right 2. Now also there are points in between, right? Because we know that a slope of -3/2 is -1.5 over 1. So you could go down 1.5, which is a little awkward to graph, down 1.5, which would be about here, over 1. So there are many other points that we're not graphing, but we know that they would be, we could find them. So we graph the easiest points to graph right now. So the other way of writing it is where the rise is 3, that's positive now. So that means that we move up, and that -2 for the run instructs us to go left 2. So let's go back to our starting point right here, and let's go up 3, 1, 2, 3, and left 2. And we can see that the pattern continues. In fact, we can instead of graphing every single point, I think we have enough now to just kind of draw that line connecting all those points. So let's end by summarizing the 4 slope scenarios you need to be familiar with. So there's the situation of a line that has a positive slope. And kind of a good way to think about that line is if you move from left to right along that line, if you were walking along that line, so here you are starting all the way to the left and beginning to walk, you find yourself going uphill. So that's a situation where we have a positive slope, right? We're walking, our x-coordinate is going from negative to positive, and our y-coordinate also goes from negative to positive. Then we have negative slope, which looks, a line would look like that. It has negative slope. Similarly, if you start with an x-coordinate all the way to the negative values and your x-coordinate starts increasing, notice that your y-coordinate decreases. You are walking downhill, so it's a negative slope. Zero slope would have a horizontal line, and you're just walking horizontally, that's effortless. Right? All run, no rise. And finally, an undefined slope that occurs when you have a vertical line, and there's no point even trying to walk up that line. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.